You got it. Like terms. So I look to see what constitutes like terms. And I recognize like terms. So I combine 6x and 8x. By the way, 6x plus 8x is 14x squared. True or false?
False.
That's right. 6x plus 8x is?
14.
Leave the x's alone. We only use the first property of exponents when we're multiplying. So this is 14x plus 20. All right. That's how the answer will show up in standard form. Is that okay? All right. Let's do the same two polynomials except subtract. And this is what your number 37 originally looked like. All right, if somebody asked you, what do I do when I have a negative in front of the parentheses, how would you put it? What would you tell them? Yes, ma'am?
Distribute it.
Distribute the negative 1. How many of you would say distribute the negative 1? Would anybody put it in another way?
Change the sign of each term.
Of each term where?
Inside of the parentheses.
Okay, so you could also express it, change the sign of every term that you're subtracting inside the second parentheses, right? Either way, you're going to get the same result. First one stays the same. Distribute the negative or change the sign of everything inside. I get either way, minus 8x, minus 15. Are you with me there? And once again, you're combining like terms. I like that one and I like that one, so they're like terms. Okay, so I get negative 2x, and I get
Minus 10.
Somebody want to ask you a question about negative 2x minus 10? Something nagging anybody? What? What's nagging? How's that going? How are we going to do that? And I think that's fine. Was that a standard you used somewhere? Okay. Anybody else use that? Polynomials only have positive leading coefficients. Okay. So depending on your text or depending on your instructor, that's sometimes. But this is perfectly legitimate. So. Negative 2x minus 10. So you shouldn't have a whole lot of problems if I'm adding or subtracting, i.e. combining polynomial expressions. It starts to get a little bit more challenging when I start multiplying, but not a whole lot. Let's take a look. Let's just multiply a monomial. Let's start multiplying a monomial times a binomial. What's the property you're going to apply here? Absolutely. And every single time you multiply polynomials, you're going to be using the properties of exponents. Don't forget those guys. They are important. 2x times 4x is?
8x.
You just use the first property of exponents. Congratulations. Minus 10x. Okay. No big deal. How about a binomial times a binomial? That's right. FOIL, right? You're familiar. Binomial times binomial. FOIL. Here we go. And you know what typically happens with a FOIL? Typically, not always, but typically, the middle two terms will be like terms and you can combine them. And that's typically. Sometimes you end up with 4 terms, because these will not be like terms. Now, just to give you a warning, everybody ready for a warning? At the end of this period and next time we're together, we're going to be talking about factoring. Okay, everybody's favorite. How many of you have been waiting for factoring? All right. So we talk about factoring. In other words, we'll start out right here. And we will remember, based on what we're doing today, that oftentimes trinomials arise from multiplying two binomials. So we're going to ask ourselves a question. Are there two binomials that I can multiply to end up with this trinomial? That's the process we're going to start today and finish up on Thursday. So we're going to be looking at this, looking at different parts of it to give us some clues, and hopefully come back to the two binomials that we're multiplying. So don't forget, ladies and gentlemen, how we arrive at this trinomial is by the multiplication of two binomials. We're going to be looking at that shortly. Okay, try another. Now, do you notice something unique or special about this arrangement here? Yes. Yeah, you can tell there's something special about this, right? What does this remind you of? Multiplying what? What are they called? Conjugates. This is like multiplying conjugates. Like 3 plus square root of 5, 3 minus square root of 5. Remember that arrangement? Do you remember what happened to the O and the I when I multiplied conjugates? They're out here. They went away. They're opposites. They add to 0. This arrangement, identical, opposite signs, is going to have the same result. Let's do the FOIL and observe it. Okay, there's minus 15x. What do you know? There's plus 15x, an opposite. There's minus 25. Just as in the multiplication of conjugates, middle two terms are opposites, so they go to 0, or we say they cancel each other out. And I get not a trinomial like that first multiplication, I get a binomial, very special binomial. What's the common name for this configuration? Difference of squares, or difference of two squares. You heard that before? You'll see it again. When we encounter it again a little later on today and Thursday, we'll say, hey, here's a perfect square minus a perfect square. Wait a minute. I remember where this comes from. This comes from two binomials multiplied, one with a plus in the middle, one with a minus in the middle, with a special look. And we're going to factor this difference of two squares into these two binomials. So keep that in mind. That guy is also going to show up often. Hey, what happens when I multiply 3x by 5, not by 3x minus 5, but by 3x plus 5 again? You think the middle two terms are going to cancel?
No.
No, not unless you got a plus and minus. So here we go, let's see what happens. 9x squared again. There's 15x again. So what do you know, there's 15 more x. There's a plus 25. And I end up with a trinomial that has a special name also. What's this guy called? Anybody got a name for it? Perfect square, absolutely. It's a perfect square. This is called a perfect square. Or it's sometimes called a perfect trinomial square, just to remind us that it is a trinomial. But But a perfect square,